Finding an inverse of a rational function. Let us look at the parent function for the rationals, y equals 1 over x. To find the inverse of this function, we know from what we've previously discussed on the process of finding an inverse algebraically is we're going to swap the independent and dependent variables x and y. So wherever I have a y, I'm going to put an x. Wherever I have an x, I'm going to put a y. Then we are going to resolve for y. So we'll multiply both sides by y, and then divide by x. We'll note that this function is an inverse by incorporating that little -1 in the exponent position. And what we notice here is that the inverse of the parent function is itself. So the inverse of 1 over x is 1 over x. Now the algebra supports that, but let's confirm through the visual. So we know 1 over x looks like the following. We have a vertical asymptote at the y-axis and a horizontal asymptote at the x-axis. And we have that piece in quadrant 1, and then we have a second piece in quadrant 3 that aligns with those asymptotes as well. And we know that that idea of swapping the independent and dependent variables is the same thing when we're working with a visual or in the coordinate plane of taking all of the coordinates that compose the function 1 over x and exchanging or flipping the x and y coordinate for each one. And what that does visually is a reflection over the line y equals x. Y equals x is a linear equation. Slope of 1, y-intercept of 0. And you can see that that graph 1 over x looks like a mirror image about that line. So it makes sense visually as well that the inverse of the parent function 1 over x is itself. Now let's get into some more complicated examples. Let's say we take -2 over x plus 5. Same process, swap independent and dependent. And let's resolve for y. So how are we going to do this? Well, y is currently in the denominator, so just like before when we moved y to the other side, we're going to move y to the other side, but it has to be accompanied with the plus 5. So we're going to multiply both sides by y plus 5. Divide by x. And then subtract 5. And there's our inverse. Another example. Swap. We solve for y. So a couple approaches here that could potentially happen. You may be inclined to multiply both sides by y at this point, or you might move the 6 first. Either way, we should get to the same place, so let's do it both ways. Let's say you multiply both sides by y. So the left side is going to be yx. The right side, remember, you're multiplying this entire side by y, so you must remember or practice that sound algebra where this y is being multiplied by the whole side, so all terms on that side must be multiplied by y, which results in 1 minus 6y. Then we want y by itself, so it would be helpful or a good idea to put all the y terms on the same side of the equation. And we have two y's here, but ultimately our goal is to get y equal. So we only want a single y, so you'll notice that the two terms on the left side both possess a y, which is a common factor amongst the two terms. So let's factor out y and leave behind x plus 6. So that gets us down from 2 y's to 1 y, and we just divide by the quantity x plus 6 to get our inverse. So that was the step-by-step if you elected to multiply both sides by y. But let's say you added 6 first, so you would get to this point, x plus 6 equals 1 over y. Then you multiplied both sides by y. Now we don't want to multiply all the terms on the left by y through distribution, so leave it as I have it formatted there. because we want to isolate y. So I don't want to distribute to both terms because that gives me two y's when we know we only want one. And that line should look familiar to what we have over here. Just divide by x plus 6, and we get the same answer. So either way will get you to the same place. Just make sure you are sound with your algebra. If you elect to multiply both sides by y first, realize that all terms on that side must be multiplied by y. Now let's jump into a slightly more complex example where we have a linear expression up top and on bottom. So we just had constant values in our numerators for the previous two examples. So let's say I had 2x plus 3 over 3x plus 7. We're going to make the swap. There's two x's on the right, so both are going to become y. Now to resolve for y, this is where we have to be clever with our algebra. So we're going to clear that denominator. Now this next part may seem counterintuitive, but it'll ultimately help us in the end. So we're actually going to distribute the x on the left because I don't want to move x to the right because now I have y's on both sides and it's going to get messy. So if I actually just distribute the x, again, which may seem counterintuitive, but it's going to help us because in this next step, we want to get all our y terms on the same side and any term without a y on the other side. So the 3xy and the 2y we're going to place on the same side, and the 7x and the 3 we're going to get on the same side because those terms don't possess a y variable. Now, just like the previous example we saw, on the left side, we have two terms that both possess a y. So we want to factor out a y. Now, don't factor out a greatest common factor. So I don't want to include any constant values with that because my goal is to just isolate y. So just be careful of that inclination that you may possess. We just want to remove a single y. And that now allows us to isolate y by dividing by 3x minus 2. And there's our inverse. Now, what you may notice is interesting about the function we started with and its inverse is that they're kind of similar in terms of the numbers we see. And in fact, there is a shortcut we can derive when we have something of the form ax plus b up top and cx plus d on the bottom. Imagine there are four numbers present in a scenario like this. You have a number in the top left, top right, bottom left, bottom right, which I will circle now. So top left, top right, bottom left, bottom right. So imagine we have these four quadrants. You'll notice on the inverse, the position of the bottom left and top right stay fixed. They're still what they were originally. We have that 3 and that plus 3 still in place. And the numbers that are in the bottom right and top left seem to have switched position but also changed signs. And that is the shortcut for a scenario when you have, and we'll prove this shortcut in a second, when we have linear expression of the form ax plus b over cx plus d, where a, b, c, and d are constants, we know the inverse, or at least we propose that the inverse will be b and c stay fixed because they are in the top right, bottom left positions. But C, A, and D swap. So top left and bottom right switch, but also change signs. So switch the signs of those two values. And that's what the inverse should be. So let's confirm that, and then we'll just do a quick example at the end. So if I have this, using the process we had before, we're going to have, this is our first step. We're going to clear the denominator. We're going to distribute the x. We're going to get our y terms on the same side and non-y terms on the other side. We're going to factor out y. And then we divide by cx minus a. And what do we get? But none other than what we thought the shortcut would be. So a really neat, short, condensed way to get a rational function inverse when we have something of the form ax plus b over cx plus d. So these expressions are linear, so just take note of that. And just to put it to application, let's say we start with something like this. So the inverse should be that 10 is going to stay fixed, that negative 12 stays fixed, that 7 moves to the top left, we got to change the sign. So it becomes negative 7, and that negative 4 goes to the bottom right, we got to change its sign. So this should be the inverse, and I will let you verify that on your own. So a nice little shortcut there, and you'll notice that all the examples we did in this video had linear or constant expressions in the positions of the numerator and denominator. So we know by definition our rational functions are a ratio of two polynomials. And we limited or restricted g to being just a constant or linear and h to being linear. And the reason we did that is because not all functions possess an inverse that is also a function. And there's some other considerations that need to be made in the event that we were to introduce polynomial expressions of higher power, which we would save for another time or another course. So we intentionally limited g to constant, linear, h to linear, so that we would be able to execute that algebraic process that we use to find inverse functions, and also to guarantee that the inverse we find would also be a function. So just wanted to make note of that if you're wondering why we didn't look at anything of a higher power for our numerator or denominator expression. So that concludes the video on how to find an inverse of a rational function.